All right, this video is part one of the angled launch projectile notes. So before we get started talking about projectiles that are launched at an angle, we need to review some background. So projectiles move in two directions. They move both vertically and they move horizontally. And this is pictured here in this diagram to the left of this horizontally launched projectile. If it's a ball that's launched off the edge of a cliff, we can see that horizontally it moves at a constant speed. And vertically, as it falls off the edge of the cliff, it moves at an accelerated speed. In fact, it accelerates by about 9.8 meters per second squared every second. So, angled projectiles are a little bit different. They're launched at an angle. So what I mean by that is they're not launched horizontally the way this picture shows, but they're launched up and to the right, which means it has two initial speeds. It has an initial horizontal speed, pictured here with this arrow, and it has an initial vertical speed, pictured here with this arrow. So you might say that a cannonball is launched with an initial speed of 20 meters per second at a 45-degree angle. That 20 meters per second can be broken down into these two components, similar to a right triangle, the way we have A sides, B sides, and C sides. The way we can maybe use Pythagorean theorem to solve for those sides, or even the way that we might use SOHCAHTOA to solve for those sides. We're going to want to be able to know horizontally how fast this cannonball is going, because horizontally we know that that speed is not going to change. And vertically we'd like to know how fast is the cannonball initially going, because its speed is going to accelerate or change vertically by negative 9.8 meters per second squared. So being able to take our initial velocity, or the C side, and break it down into a horizontal component and a vertical component will be very helpful for us in describing the motion of a projectile, in this case the cannonball, being launched at an angle. So let's talk about how we would go about solving for horizontal and vertical sides. We're actually going to use our SOHCAHTOA skills in order to do this. So for example, let's say a projectile is launched at a 20-degree angle with a speed of 40 meters per second. The first thing that I would do to solve for my horizontal and vertical speeds of this projectile is draw my launch, I should say. 20 degrees means that it is a 20-degree rotation above the horizontal axis. This initial launch speed of 40 meters per second is referring to the hypotenuse, I should say, of this triangle that I've kind of drawn here. And my horizontal and vertical speeds are the two different sides of my triangle. So I'm going to be using two trig functions in particular, sine and cosine. The sine function relies on the opposite side of my angle, which is my vertical speed, and the hypotenuse, which I know to be 40 meters per second. So if I were to plug in and solve, I would substitute in maybe Vy for my vertical speed for my opposite side, and 40 for my hypotenuse for my 40 meters per second. Now Vy, my vertical speed, would be the variable that I'm solving for. So whatever I'm doing to Vy in this equation, to solve for Vy, I have to undo it. So right now, if I look at what's happening to Vy, it's being divided by 40. That's what this fraction bar means. So in order to undo that, I'm going to multiply by 40. But whatever I do on one side of the equal sign, I also have to do on the other side of the equal sign. So what I'll end up happening is that 40 will cancel on the right side of my equation, and Vy will equal 40 times the sine of 20 degrees. Vy. Now it's not wanting to work. There it goes. Vy. So I just need to plug this in my calculator. So let's find my graphing calculator with my trig functions. I'm having trouble finding it. Calculator, there they are. Perfect. I like this one for whatever reason. Okay, so 40 times the sine of 20, and I'm fairly certain I'm in degree mode. Let's hit equals. Yep. So I get 13.7, let's say. So that means 13.7 meters per second is my initial vertical speed, my initial vertical velocity. Now, the other trig function that I'm going to use is the cosine trig function. Cosine is equal to my adjacent side, which is my horizontal side in this case, over my hypotenuse, which I know to be 40 meters per second. So if I wanted to substitute in and solve, I know that the cosine of 20 degrees would equal my horizontal speed, which I'm just going to label as Vx, over 40. Now again, I'm going to solve for Vx the same way I solve for Vy. So I'm going to undo that division of 40 by multiplying by 40 on both sides of my equal sign. That will effectively cancel, leaving Vx equal to 40 times the cosine of 20. I just need to plug this into my calculator and figure out what the 40 times cosine of 20 is. 20 equals, and I get 37.6. So my initial vertical speed is horizontal speed is 37.6 meters per second. So my two components are here and here. So let's move on and do one more example together. So let's say in this example, projectiles launched at a 45-degree angle and a speed of 50 meters per second. So again, if I were doing this, the first thing I would do is draw my launch. So I would draw my 45-degree angle, and I would draw my launch speed as my hypotenuse of my triangle. And remember that my vertical speed is in blue here, and my horizontal speed is in red there. So my sine function is going to be equal to the opposite side of my angle, which is this vertical side, divided by my hypotenuse. And my cosine function is equal to the adjacent side to this angle, which is the horizontal speed, also divided by my hypotenuse. So I just need to plug in my values into both of these equations and solve. So the sine of 45 degrees is going to equal my vertical speed divided by my hypotenuse, which is 50 meters per second, which I'm just going to leave 50. So I'm going to undo what's being done to Vy by multiplying by 50 on both sides. So all I have to plug in my calculator is 50 times the sine of 45 degrees, which I'll do in a moment. Vy, perfect. Now I'm going to plug in solve for my cosine function. So I know the cosine of 45 degrees is going to equal my horizontal speed divided by my hypotenuse. And I'm going to undo the divide by 50 by multiplying by 50 on both sides. And when I do that, I'll just have to figure out what's 50 times the cosine of 45 degrees, because that will equal my horizontal speed. So I know exactly what I need to plug in my calculator, so let's go ahead and do that and see what we get. So 50 times, 50 times the sine of 45 is 35.4, and let's do 50 times the cosine of 45. Oh wow, I get the same thing. In fact, I should get the same thing. You see, a 45-degree angle produces what's called an isosceles triangle. What I mean by that is the two legs of the triangle are congruent. So whenever your angle is 45 degrees, your vertical speed is going to equal your horizontal speed. Essentially, what's happening here is that my launch speed, when launched at a 45-degree angle, is split evenly between my vertical and my horizontal components. That angle of 45 doesn't produce a greater vertical launch, and it also doesn't create a greater horizontal launch. It's exactly in the middle. So my speed is split up perfectly between these two components, vertical and horizontal. So I should get 35.4 meters per second when I calculate both of them. Now, that being said, it would be wise to still calculate both of them just in case you made a mistake in one of your equations. You should get the same answer, but if you don't, that would be an indicator that you made a mistake somewhere along the way in one of your calculations, and that would be an opportunity to go back and fix it. So that being said, there's a try here. Go ahead and pause the video and attempt it without my assistance, and when you're ready to check your answer, unpause the video. All right, I'm going to assume that if you're listening to this, that means you're ready to check your answer. So we've got a projectile launched at a speed of 30 meters per second and a 60-degree angle. So hopefully the first thing you did was draw your scenario. So we've got a launch speed of about 60 degrees, something like this. Gosh, it's so small though. I wonder if I could make it any larger. Let's see. Resize. I wonder if I can make this any larger. It'll have to do. So this is a 60-degree angle. My horizontal speed is on this side, Vx, and my vertical speed is on this side, Vy. And I wonder if I can move that. Perfect. And my launch speed was, what did they tell me again? 30 meters per second? Perfect. So I know that the sine of 60 degrees is going to equal my opposite side over my hypotenuse. And I know that my opposite side is my vertical speed. And I know that my hypotenuse is 30 meters per second. So I'm going to start plugging and chugging into that. So sine of 60 degrees equals Vy over 30. I'm going to solve for Vy by multiplying by 30 on both sides. And when I do that, let's see what 30 times the sine of 60 gets me. 25 point, oh gosh, that rounds up to like 30.0. Oh wait, no, not 30, 26.0. So that's what I'm going to write. 26.0 meters per second ends up being my vertical speed. Now I'm going to use my cosine function. So I know cosine of 60 is going to equal my adjacent side divided by my hypotenuse. I know the hypotenuse is 30, and my adjacent side is my horizontal speed. So I'm going to plug into this function Vx for my adjacent side and 30 for my hypotenuse. And then I'll just multiply by 30 on both sides to get Vx by itself. And I'm going to make a prediction. I think that 30 times the cosine of 60 is going to get me 15. But that's just my guess, if I'm remembering trigonometry well. Oops. Wait, did I do that right? Yeah. 30 times trig the cosine of 60. Yep, 15. I do remember my trig. Okay, so 15 meters per second is my horizontal speed. Oops, that didn't complete the box. Perfect. So that completes part 1 of this lesson, which is just figuring out how to solve for horizontal and vertical components of the initial launch speed of an angled projectile.